So, as we discussed in the previous lecture, heat can be thought of as a transfer of internal energy from one object to another as a result of a temperature difference between these two objects. Heat is not energy itself, okay, but is rather a transfer of energy. But this raises some questions. For example, how does energy get transferred from one object to another? Okay, what is the mechanism by which energy gets transferred on a microscopic level? Okay, and are there different ways in which energy can be transferred? Well, these are some of the questions that we will talk about today, okay, in this lecture on energy transfer mechanisms. So as this matte graining cartoon nicely illustrates, in a typical day here on Earth, you will witness many different methods of heat or energy transfer. Okay, today we will talk about three methods by which internal energy can get transferred from one object to another, namely conduction, convection, and radiation. So in answer to his father's question, okay, the beach sand is primarily warmed through the process of radiation, while the warming of the water in the clam pot is accomplished mostly through what we call convection. The actual cooking of the clams, however, is due mostly to another method of heat transfer called thermal conduction, or sometimes just called conduction. So in this video, we'll explore the differences, okay, in each of these methods of internal energy transfer, what we call heat. So this is what I call doing something cool with a cigarette. Everybody knows that smoking cigarettes is not cool, but magic tricks are always cool. So I'm going to actually show you a magic trick, and I know they say that a good magician never reveals his tricks, okay, but I want to show you the trick, so if you wanted to perform it, you could. And you might learn something about thermal conductivity in the process. So notice here, if I take a lit cigarette, okay, and it is lit, if I hold it next to a piece of cotton cloth, okay, I'm going to put it behind the cotton cloth here. All right. Now, given enough time, what you would expect reaches the combustion temperature of the cloth, puts a hole right through the cotton cloth. Okay, so this is where the magic comes in. You need to perform this, okay, the same way, but this time take a coin, like this quarter here, okay, very slyly get it behind the cotton cloth. Okay, that's where the magician comes in. And notice this time that when I do the same thing, okay, when I hold this lit cigarette to the cotton cloth with the coin behind it, okay, you will notice that it is not going to burn a hole in that cotton cloth. Okay, and if you think about what you know about thermal conductivity, you know that the high thermal conductivity constant of that metal coin is going to take the heat away from the cotton cloth, okay, sufficiently so that it will never reach its combustion temperature. So here, okay, you will notice cigarette still lit. Okay, you'll notice that looks like I see a little bit of tobacco, nicotine residue on there, but absolutely no hole in that cotton cloth. Okay, so doing something cool with a cigarette. So in this slide, we will attempt to define this method of heat transfer, energy transfer that we call thermal conduction. We will also try to explain what's going on in this process from a microscopic perspective. So let's start with the definition. We can think of conduction, okay, as a method of internal energy transfer that happens because of a temperature difference. All forms of heat transfer, okay, or energy transfer occur because of a temperature difference. So a method of internal energy transfer where particles transfer kinetic energy by colliding with neighboring particles. So I think that the best way to try to understand what's going on from a microscopic perspective is to take a look at a specific example. So let's take a look at the example of a silver spoon and some hot soup. You may have had this experience before in life. If you put a metal spoon into a hot bowl of soup, okay, the end of the spoon that you're holding does not start out hot. Okay, it is much colder than the soup itself. Okay, but given enough time, okay, the end of the spoon that you're holding will warm up. Okay, suggesting that energy, internal energy from the hot soup is being transferred, okay, down that spoon handle to your hand. So what's going on here? Well, think about it. Those fast-moving water molecules in the soup are colliding with the slower-moving silver atoms in the spoon. And in the process of those collisions, they transfer kinetic energy. Those silver atoms then collide with their neighboring silver atoms, okay, which are moving slower, and in the process of those collisions, transfer kinetic energy. So this process of kinetic energy transfer via collisions, okay, with neighbors continues until the kinetic energy has been transferred really from the ladle end of the spoon all the way down to the handle end of the spoon, okay, that you're holding. And in which case, you know, at the start of the process, the water molecules are moving fast, okay, but the silver atoms were in the part of the spoon you're holding are not. But, okay, when kinetic energy is being transferred, eventually those silver atoms in contact with your hand are moving fast as well. So you can kind of see this in the simulation here. It's not great, but water, symbolized with these red particles here, okay, are moving fast, and you see that by colliding with these slower moving blue silver atoms in the spoon will transfer energy until, okay, eventually all of the particles are moving quite fast. We'll take a look at this illustrated here. Here's another, okay, animation to see this. Again, not great, but when it starts from the beginning, you'll see that the particles near the hot source, a high temperature object, gain kinetic energy, and through this process of particle collisions, this kinetic energy gets transferred down the rod. Okay, here's something you know, that if you put a pan in a stove, okay, initially it's no problem, but eventually, okay, because of this transfer of kinetic energy through molecular collisions, the handle of the pan in contact with your hand will get hot. Why? Because those particles there will start moving fast after, okay, the kinetic energy has been transferred to them through this process of particle collisions. A really great analogy to help understand this process of thermal conduction from a microscopic point of view is that of the domino effect. And if you have a stack of dominoes lined up, kinetic energy is given to that first domino of the stack, okay, and that is it, the start of the process, the only domino that has any kinetic energy. Okay, but when that domino collides with its neighboring domino, it transfers its kinetic energy to its neighbor, okay, and then that neighbor transfers kinetic energy to its neighbor, and so on, so that kinetic energy gets transferred all the way down the stack of dominoes. Okay, note that while energy gets transferred from the first domino to the last domino, okay, the first domino never interacts directly with the last domino. Okay, so while the energy actually gets transferred, okay, matter or particles do not. Okay, so this nicely illustrates what is going on in the process of thermal conduction. So when you think about it, the process of energy transfer via thermal conduction has a lot in common with the energy transfer taking place in a mechanical wave. Okay, in a mechanical wave, energy is added to the medium, okay, by a vibrating object, okay, like this speaker you see in this simulation. That vibrating object causes the particles in contact with it to vibrate as well. And because of the physical connection between the particles in the medium, these particles, okay, cause their neighbors to vibrate and so on. So that this microscopic kinetic energy gets transferred along the medium in what we call a mechanical wave. I would say that the only real difference between these two methods of energy transfer, okay, that is between the mechanical wave and energy transfer via thermal conduction, okay, is that the vibrating object causing a mechanical wave, okay, involves a very regular, periodic, ordered motion, so that the particles in the medium vibrate in a very regular, ordered, and periodic fashion. In the case of internal energy transfer by thermal conduction, however, the motion of the particles in the medium is much more random, much more disordered. Okay, so while energy is certainly transferred along the medium in both cases, okay, it is not done so in the case of thermal conduction in such an orderly way. So you see there is a slight difference between these two processes, but they certainly do have a whole lot in common. So we now want to describe a macroscopic model for this process that will allow us to make actual measurements and make some predictions about, okay, the rate of energy transfer via thermal conduction. I say this is an empirical model because the physical law that we're going to come up with is based purely upon, okay, empirical experiments. So before we actually state the law, let's just take a look at our starting point here. And I think we will be in agreement that we can basically predict the law, okay, just from common experiences in life. So, okay, what we're going to do is we're going to consider heat flow, really internal energy flow, due to a temperature difference, okay, through a uniform slab of length delta x and cross-sectional area A. So what we have here, we have two temperature reservoirs. Okay, this reservoir I'm calling T high. This is our high temperature reservoir. Okay, our low temperature reservoir we'll call T low. The slab, okay, has a length delta x, and it has a certain cross-sectional area. So the slab is really this portion right here, okay, just in contact with these two temperature reservoirs. It is thermally insulated so that no energy can escape through the sides of the slab. And obviously the direction of energy transfer, okay, we'll say heat flow, even though this is a bit of a misnomer because the word heat implies the flow of energy. Okay, but we still use this term heat flow, is from the high temperature reservoir to the low temperature reservoir. So what sort of factors would affect the rate at which energy gets transferred, okay, from one end of the slab to the other? So our prediction here, well, how do you think the difference in temperature across the ends of the slab will affect, okay, the rate at which energy gets transferred? Hopefully you would agree that there should be a direct relationship, okay, that the bigger the temperature gradient, okay, the more energy will get transferred per unit time. So that would be a direct relationship. In terms of the cross-sectional area of the slab, we could say the same thing. Okay, and I don't really show you that here, but this measure right here is really the two-dimensional cross-sectional area. So as the slab gets thicker, as that cross-sectional area gets bigger, we would expect that more energy can move along it per unit time. There should also be a direct relationship. When it comes to the length of the slab, however, okay, we would expect the opposite. We'd expect an inverse relationship. Okay, because what is prompting the energy transfer, the heat flow, are these two different temperature reservoirs. Okay, so the greater the separation distance between them, okay, the longer amount of time it's going to take for that energy transfer to take place. So we would expect an inverse relationship, okay, as that slab gets longer. And finally, the thermal conductivity, this is really a proportionality constant that takes into account that Some materials happen to be better thermal conductors than others. And so we'll talk more about that in the next few slides. But the way we define thermal conductivity, we define it to be in such a way that there will be a direct relationship between the rate of energy transfer and the thermal conductivity. So given our predictions on the previous slide, we're now in a position to state this empirical law of thermal conduction. So for a macroscopic slab thickness, and it's what I'm showing you again on the bottom left-hand portion of your screen, macroscopic slab thickness delta X, the power, the rate at which internal energy is transferred by this method, called thermal conduction, the empirical law looks like this, minus Ka delta T over delta X, where, remember, K is a thermal conductivity constant, A is the cross-sectional area of the slab, delta T, that is the temperature difference between the hot temperature reservoir, high temperature reservoir, and the low temperature reservoir, and delta X is a slab thickness. Notice that we put the minus sign here. That indicates that heat flow, the direction of the energy transfer, is opposite to the direction of increasing temperature. So when we define delta anything, like in this case delta T, it's always final minus initial. So here, if an object ends up at a higher temperature than it starts at, that would give you a positive value for delta T. But that would also indicate that heat would flow from the cold object to the hot object if that object was going to end up at a higher temperature than it started out at. That's why we put in the negative sign. This indicates that the heat flows in the opposite direction, to the increase of temperature. If we want to define this same law, but from the perspective of infinitesimal changes in, let's say, slab thickness, dx, then we can simply make this substitution. We let our deltas, our macroscopic changes become microscopic changes, and our deltas become differentials. So here, by making this substitution, delta Q becomes dQ, delta T dt, in which case, we're now taking the instantaneous rate of energy flow, and delta T over delta X becomes dt dx. dt dx is what we call the temperature gradient. It shows you how the temperature, changes with position here, in a microscopic or very small scale fashion. So in this slide, we will now turn our attention to this thermal conductivity constant, this thing we call K in our law of thermal conduction. So remember, we said previously that the thermal conductivity constants are material dependent, that they depend upon the type of material. So if we take a look at this table, this will show us some values for thermal conductivity constants. And you'll notice here in the upper left-hand portion of the table, we have some metals. And you'll see that in comparison to the other materials, metals tend to have high values of thermal conductivity constants, which means that the rate at which metals can transfer energy via thermal conduction is better than for most other materials. They have a higher rate of energy transfer via thermal conduction. So if we come down here, we will see that not all metals are created equal. However, look at how high the value is for silver, for example, compared to that of lead. Silver is much more effective. It can transfer much more energy per unit time, via thermal conduction than can lead. If we come over here, we look at water, we see, well, water has a thermal conductivity value that's much, much less than most metals, but is certainly much greater than
Okay, the thermal conductivity value for air down here. Notice how small that is. And that is what makes clothing so effective. Believe it or not, your clothes work to keep you warm in the wintertime, not because of the material the clothes are made out of, but mostly because of their ability to trap air, because air, it turns out, is such a good thermal insulator, having such a low thermal conductivity constant value. So basically your clothes work, they trap a layer of air against your body, which means that the rate of energy transfer from your body to the colder environment, okay, is greatly diminished because of that low value of K. This brings us to define what we mean by thermal conductors versus thermal insulators. So I think it would make sense that a good thermal conductor would be a material with a large K value, whereas a good thermal insulator would be a material with a small thermal conductivity constant value. What is it that actually makes a material a good thermal conductor as opposed to a good thermal insulator? It has to do with the ability of those particles to move. Think about what's happening in the process of thermal conduction. Okay, you have the transfer of kinetic energy due to particle collisions. Well, if the particles can move very easily, okay, then that would suggest that they will be very effective transmitters or transferers of kinetic energy. Okay, and it turns out that metals, because those electrons are very loosely held, okay, by the atoms in the metal, those electrons have a lot of mobility. That makes metals good thermal conductors. And by the way, when you take Physics 103, you will see that it is exactly the same reason that makes metals good electrical conductors as well. Okay, the fact that those electrons in metals are very free to move. Whereas a good thermal insulator would be one where the particles don't move easily. Think about it, if those particles cannot move easily, then their ability to transfer kinetic energy is greatly diminished. Okay, and the rate at which energy will get transferred along that material will be much less, okay, than for the case of a material where the particles making up the material can move quite easily. This animation nicely illustrates the difference between a material with a low thermal conductivity and one with a high thermal conductivity. Notice that the rate at which energy gets transferred along the slab of aluminum nitride, a material with a high thermal conductivity, is much greater, okay, than the rate at which energy gets transferred along the slab of zirconia, okay, material with a much lower thermal conductivity.
All right, so folks, what we're going to demonstrate here is thermal energy transfer by conduction, this process that we call conduction. And to demonstrate this for you, I have two blocks, two little slabs, which may appear to be the same to your naked eye, but it turns out that the slab I'm pointing to right now is solid aluminum, okay, whereas the slab that I'm now pointing to is plastic. It turns out that aluminum has a much higher thermal conductivity than does plastic, which will make it a much better thermal conductor. Now, in the process of conduction, we're going to see that heat is going to get transferred from each of these blocks to the ice, and it's going to melt the ice. And we will see that because aluminum has a much higher thermal conductivity, we will see the much faster rate at which the conduction process takes place. So we see here how quickly this ice cube is melting over here with the aluminum block, okay, as opposed to the plastic block. When we talk about this conduction process, remember we're saying that on a microscopic level, okay, the atoms of aluminum, which have a high kinetic energy because of a higher temperature than the ice, are colliding with those water molecules in a solid state. That is the water molecules in the ice cube. And when they do that, they transfer a little bit of their kinetic energy. And this then causes the kinetic energy of those water molecules to transfer kinetic energy to adjacent molecules, and so on down the line. So we see that aluminum is a much better thermal conductor than is plastic. And you may know that if you put your hand inside of an oven and you happen to just touch the air in the hot oven, you're fine because of the low thermal conductivity of air. But if you happen to touch the sides of the oven, okay, because of the very high thermal conductivity of the metal, okay, it's much easier to get burned. You have a whole lot more heat transferred to your hand. So we've talked about factors that affect the rate of thermal energy transfer by conduction. We said that the rate of heat transfer via conduction depends upon, okay, the length of our slab, okay, depends upon the cross-sectional area of our slab, depends upon the temperature gradient that exists across the slab, and it also depends on this property of the material that we call the thermal conductivity constant. So in this demonstration, we're going to study the effect of the thermal conductivity constant on the rate of energy flow, okay, the rate of heat transfer by conduction. So let me get this lid and I'll explain a little bit about, okay, the setup here. Okay, and you'll see here that what we have is we have 5 different rods. Think of them as slabs. They all have the same length. Okay, they all have the same cross-sectional area. They are all going to be subjected to the same temperature gradient, which I'm going to, by placing this Bunsen burner here in the middle, we'll see that the ends of the rods that are near the Bunsen burner, okay, will be at the same high temperature. The other ends will be the room temperature environment. The only thing different about these rods is the material they're made out of, and therefore their thermal conductivity constant. So the rate at which heat will flow down these rods will affect, okay, how quickly the temperature of the ends reaches a point, as we saw here, where the actual candle, to melt the wax and allow the candle to fall out. Okay, so we see here that this particular rod, okay, had the highest thermal conductivity constant. This one over here, the second highest thermal conductivity constant. Okay, and we will see that, you know, the temperature required to melt the wax and make the candle fall, they will all reach that temperature, but not at the same rate. Okay, so we see here the rate at which thermal energy gets transferred changes, okay, as a property of the material itself. So I think we'll wait for one more of these to fall, and then we can okay, probably quit the demonstration. We get the idea here. Okay, we see that the greater the thermal conductivity constant, the greater the, okay, rate of heat transfer by thermal conduction.
So let's take a look at applying this empirical law of thermal conduction to a quantitative problem where we perform some calculations. So in this problem here, we will explore the heat loss through windows, okay, where we're told that in Bago's bedroom window here, we're given some information about the dimensions of the window, the width, the height, and the thickness. Remember, we're going to treat the window as a slab, okay, so the thickness, the 3 millimeter thickness, is really what we're going to consider delta X in our formula. And we want to calculate the rate of heat flow through the window on a cloudless night, given that the inner and outer surfaces are 14 degrees Celsius and 16 degrees Celsius. Notice here that the temperature of 16 degrees Celsius, that inside temperature, is much lower than that of the room, okay, and the outside temperature of 14 degrees Celsius is going to be slightly higher than the outside, okay, temperature of the environment. So in order to apply the law of thermal conduction, we need to identify the cross-sectional area, okay, the slab thickness, as well as the thermal conductivity constant. So the cross-sectional area is just the width times the height, okay, 2 meters squared. The slab has a thickness, the window thickness is 3 millimeters or 0.003 meters. And we have to look up in our table the thermal conductivity constant for glass, which is 0.8 joules per second meters degrees Celsius. Okay, and we are now ready to figure out this rate of heat loss by substituting into the law of thermal conduction here. Okay, we plug in our numbers, and our temperature gradient, recall here, delta T is going to be the difference between the inside and outside temperature here. And we come up with a rate of heat loss of, okay, having a magnitude of 1100 joules per second. Follow-up question here, what is the physics behind double-paned windows? Well, you see here that air acts as an excellent insulator, okay, that's true, but whenever you have a little bit of wind, okay, a little bit of airflow, okay, the wind causes the air that is warmed, okay, to be replaced by the cool air. Okay, this basically is what we call wind chill factor. If you had very still air, and like we talked about clothing, the purpose of clothes is to trap that layer of air against your body, then the air can do its job. It can behave as a very good thermal insulator. But the problem with windows, while the air on the outside is a good insulator, it continually gets replaced with new colder air. That's the problem. So the double pane windows, all they really do, just like clothing, they trap a layer of air that doesn't get replaced. You'll see that, nowadays in your even more expensive windows, you can buy windows that have the casing not filled with air, but filled with a low pressure gas that is even a better insulator than air, with a lower thermal conductivity constant than air. If the window casing could get totally evacuated, okay, then there could be no possibility of heat loss via thermal conduction, because remember that conduction requires a medium. So one of the ideas is to, if you can partially evacuate that window to remove most of the matter, okay, now you're really, okay, lowering the rate of heat loss due to thermal conduction. You're making the thermal conductivity constant very, very small. So we will now take a look at some conceptual examples, okay, no calculations required, where we have to apply these concepts that are present in our empirical law of thermal conduction. So we'll start by explaining the demonstration that you saw at the beginning of this lecture, okay, where a cigarette was allowed to burn a piece of cloth. It quickly brought up that cloth to its combustion temperature, okay, Fahrenheit 451, roughly, when the cloth was just exposed to the air. But you recall when there was a metal coin placed behind the cloth, okay, there was no possibility of getting that cloth up to its combustion temperature. So because that metal coin is such a good thermal conductor with a high thermal conductivity constant, okay, the rate at which it was able to remove heat from the cloth was sufficient to prevent the cloth from ever reaching its combustion temperature. One more conceptual example here. Taking a look at tile floors. Why is it that your feet feel much colder on a tile floor than on carpet in the wintertime, when both are really at the same temperature? I mean, think about it. You may have a house that has both carpet and tile, and the temperature of both carpet and tile are going to be whatever that temperature is of your room. Yet it's much less comfortable to be standing on tile than it is a carpet. Well, just so you realize, it's not that the tile is at a lower temperature. Think about thermal conductivity. The tile is a much better thermal conductor than the carpet, which means that it allows heat transfer from your feet, okay, to the environment to take place at a much higher rate than when you're standing on carpet. And this causes that sensation of feeling cold. It's not the temperature per se, it's really the rate at which your body is losing thermal energy, okay, losing its internal energy. And the greater the rate of heat loss, okay, the colder your feet are going to feel. So let's take a look at applying this empirical law of thermal conduction, okay, to a few examples, and we'll start by looking at some qualitative or conceptual examples. So this first example, I think, is something that most of you have experienced at some point in your life, and that is after basking in the sun at a swimming pool, you jump in the pool thinking this is going to feel so good because you're hot, okay, but your sensation upon jumping in is that, okay, it's very cold, and your reaction is to want to get out immediately. But if you stay in the water for a little while, okay, you realize, yeah, it's not so bad once you get in. Okay, so what's the physics behind this? Well, if you think about it, after basking in the sun, your skin temperature is quite high. Okay, so that when you look at the difference in temperature between your skin and the pool water, that larger temperature gradient means that when you jump in the water, your body is going to be losing energy to the water via thermal conduction at a much faster rate, okay, because of that high temperature difference. Your sensation of feeling cold has a lot more to do with the rate at which your body is losing energy to the environment, okay, than it does with your actual body temperature itself. So when you think about it, after you've been in the pool for a little while, your skin temperature lowers, okay, which means the temperature gradient or temperature difference between your skin and the pool water is lower, so your body stops losing energy at such a fast rate, in which case you don't feel so cold. The second example, okay, let's see, fire walking. No, that's not what I mean. Okay, we're talking about, okay, the act of being able to fire walk across hot coals. Okay, what's the secret behind it? Okay, well, okay, if you think about it, okay, coals are made out of wood, and the thermal conductivity of wood is quite small. Wood acts as a good thermal insulator. So even though the temperature of the coals may be quite high, because the wood is a good thermal insulator, not much thermal energy is going to get transferred to your feet, okay, by means of thermal conduction. Okay, an example that you could probably relate to a little bit more, I doubt many of you have had the experience of walking across hot coals, but think about what happens when you stick your hand into a 450 degree Fahrenheit oven. If all you touch is air, which is a good insulator, you're not going to burn your skin even though you're coming in contact with the air, which is at 450 degrees. But if you touch the metal part of the oven, ouch. Okay, even though that metal is at the same temperature as the air, because metal is such a good thermal conductor, okay, the rate at which energy will get transferred to your body, okay, is much greater than for the air itself, okay, which will certainly cause you a burn. So we're now going to turn to our second method of heat flow, really more correctly defined as energy transfer mechanism due to a temperature difference. And this is the method that we call convection. So to motivate our discussion, we're going to take a look at a sort of cool demonstration here. This is what I call the rising water mystery, and you'll see it in the next slide. And as you're watching it, try to think about this. How can the differences in the arrangement of the bottles, and you'll see here in both setups we have a hot and cold bottle of water, the difference being whether the hot bottle or the cold bottle is on the bottom or the top. How can these differences help explain, okay, what you observe?
All right, so folks, what we have here is an arrangement of bottles, and this is a nice way to see convection in action. And although things may look very similar to you, it turns out that what we have here, the bottle I'm touching right now, this is hot water, okay, whereas the bottle above it is cold water, okay, just as in the diagram on the PowerPoint slide, whereas over here, this one happens to be cold water, whereas the one above it is hot water. Now right now there's no mixing that can take place between the bottom bottle and the top bottle because I've got these pieces of transparency acetate that are preventing mixing. But I'm now going to pull these out so that we can allow the mixing to take place. Okay, and this, boy, that is hot. Okay, so I pull that out so the mixing can take place. This one will be easier because it's colder. And then we are just going to watch what happens and see how much mixing takes place. Now, as we see that mixing take place, you will notice that it is convection, okay, natural convection that is responsible for this mixing. And the fact that hot fluids are more buoyant than cold fluids causes them to rise up, okay, because as their as their temperature increases, they become more buoyant with a change in density. And you will see that when we have the hot water on the bottom, the cold water on the top, the natural convection that takes place, okay, as that hot water rises up, okay, we can tell because that food coloring is mixing quite a bit. When we have the inverted bottle here, we see that the cold water on the bottom is more dense, less buoyant than the hot water above it, so we don't get any of this natural convection to take place. We don't get any natural mixing. So this is happening in the atmosphere around us all the time, okay, when it comes to air and other fluids like water. But by putting a few drops of food coloring in this, we can see these convection currents that get set up in one case and don't get set up in the other.
So, cut?
I think the mixing is good.
So we will certainly come back and explain the demonstration, okay, after we talk a little bit about, okay, this method of heat transfer, okay, convection. So if we try to understand microscopic explanation of the convection process, okay, we can say that convection is a method of heat transfer, really energy transfer, okay, by the mass movement of particles from one place to another. When we contrast convection with conduction, okay, how does the molecular motion in convection differ, okay, from the molecular motion in thermal conduction? Well, you see here that in conduction, the molecules don't move over large distances, right? The molecules vibrate back and forth, collide with their neighbors, transfer some kinetic energy, okay? And in that sense, we likened conduction, that transfer of energy, to a mechanical wave. The particles in the medium move, okay, but there is no net motion of the particles. In convection, however, okay, there is net motion of the particles. Okay, energy gets transferred by the mass movement of particles through space. So recall that we said that in our discussion of wave theory, there's really two ways in which energy can be transferred between one point in space and another. Okay, the first way is through particles, the second way is through waves. Well, so we're finding out here that convection really involves the transfer of energy through space via particles, whereas we said thermal conduction involves a transfer of energy through space via mechanical waves. So convection involves the transfer of internal energy, okay, from a high temperature environment to a lower temperature environment through the mass movement of matter, okay, the mass movement of particles. So the question is, what is it that makes these particles move, okay, from a high temperature region to a low temperature region? It turns out there's really two different mechanisms, okay, or I should say types of convection. The first is what we call forced convection, and we'll start by taking a look at that because it's the easiest to understand. So the mechanism to make those particles move from the high temperature area to the low temperature area, when we talk about forced convection, the mass movement of particles results from either the action of a fan, okay, or a pump. So we'll take a look at a couple of examples here. Certainly if you look at the forced air heating system in your house, this happens because you have a fan which will physically blow high temperature air particles, okay, that are heated over some type of heater. It will physically blow them through the duct system in your house to other regions of your house, okay, transferring, okay, molecules of air with a lot of kinetic energy into regions, okay, where the air has much less kinetic energy. So you can see that internal energy is getting transferred from a high temperature region to a low temperature region by having a fan physically move these particles. Similarly, in the case of a water heating system in a home or a pool, okay, it's the same concept. You need some mechanism to actually heat the water. So if you're using a solar powered system, okay, a rooftop solar powered system for your pool, okay, you then have a pump which will physically move those high temperature water particles, okay, from your roof into the lower temperature region, okay, of the swimming pool. So the second type of convection that we'll talk about, okay, the more difficult one, is what we call natural convection. And you might surmise that natural convection happens for natural reasons. Remember that forced convection, the mass movement of particles from one point in space to another, happened under the action of a fan or pump. So you can think of that as kind of an unnatural reason. Whereas in the case of natural convection, we're saying that this mass movement of particles from the high temperature region to the low temperature region happens for a reason that is more natural, that we'll take a look at. Really, we can say that the reason, the root cause, is a temperature gradient. There must be a difference in temperature between two regions in space to have any kind of heat transfer. But we will say that natural convection happens when the mass movement of particles results from either differences in pressure or differences in molecular density that cause the diffusion of particles from a high pressure region, okay, or a high density region to the low pressure region or the low density region. We will look very specifically at examples, okay, that involve this. I want to distinguish between two similar but slightly different forms of convection. One we call convection, the other advection, okay, that still fit our definition of convection. They still involve a mass movement of particles from one place to another, okay, yet to distinguish between these two concepts, when we talk about convection, we're talking about fluids, that is gases or liquids, that move in a vertical direction, as opposed to advection, where the fluids, okay, the gases or liquids, are moving in a horizontal direction. So when we say what causes the fluid motion, well, ultimately it's a temperature gradient, okay, but more directly, what would cause a fluid to move in a vertical direction? Well, let's revisit when our discussion of fluids when we talked about buoyancy and Archimedes' principle. If for some reason that temperature difference causes a fluid, either a liquid or a gas, to become more or less buoyant, okay, this will cause the particles to either move, upwards or downwards. So buoyancy, okay, when we look at the large scale movement of particles, changes in buoyancy, okay, can certainly account for the particle motion in a vertical direction. When it comes to advection, what is it that's going to cause particles to move in a horizontal direction? Well, again, it's always going to be temperature gradients that are the root cause, but those temperature gradients can lead to differences in pressure or density, that is pressure density gradients, due to the unequal heating of the fluid. And we will look at some examples of this as well. So common examples of convection, thermal uplift, okay, when you look at many birds and glider pilots, okay, we can see the mass movement of warmed air that rises upwards, okay. Even heating water in a pot. While it may be thermal conduction that heats the bottom of your pot, when it comes to the liquid itself, the water, what causes the heating of the water? It is mostly going to be due to convection. And in the case of advection, we'll take a look at, at wind. We'll look at the delta breezes that form, that results in the transfer of matter, from one region to another. All right, so let's see if we can use what we just said about natural convection to be able to explain the rising water mystery. So as you see, because of natural convection, warm water will be less dense than cold water and therefore more buoyant, causing warm water to want to rise up. So you can see here that for the arrangement of the bottles where the hot water was on the bottom of the arrangement, cold water on top, there is now a reason why those fast-moving water molecules, would want to move vertically upwards and cause mixing in the cold water region. It's because this hot water is, more buoyant, is less dense than the cold water above it. And this difference in, molecular density, difference in buoyancy, will allow for the vertical mixing to occur. For the arrangement over here where the cold water was on the bottom and the hot water was on the top, there's absolutely no reason for any vertical mixing to occur. Those hot water molecules can rise upwards, but the cold water molecules, being more dense, and less buoyant, have no reason to want to mix into the hot water region. They stay exactly where they are. You get no convection. You get no mass movement of particles from one region to another that is caused by this difference in temperature. So let's take a look at some other examples involving natural convection. And the first example we'll take a look at is really a result of advection. And this is quite important to us. This is the formation of the delta breezes, which do a lot to cool Modesto in the summertime. So this doesn't just apply to delta breezes. This applies to, ocean breezes of any types, or, really in a sense, wind that happens over land. So let's take a look at the coast. What I'm showing you on the screen here is Santa Cruz. And if we consider the summertime, the sun is beating down, but remember our discussion of specific heat capacity. We said that although the sun is beating down on Santa Cruz in the summertime, that water can absorb a lot of that energy from the sun, because of water's high specific heat capacity, without raising the temperature of the water and air in contact with it by very much. So what this means is that the temperature of the air in Santa Cruz, is going to be much lower, meaning that the density of the air and the pressure of the air in Santa Cruz will be much higher than it will be inland. So let's now come over here to Modesto. Inland, where we have the sun beating down on the land. Much higher air temperature means that the density of the air and the air pressure are going to be much lower than they would be in Santa Cruz. This difference, this gradient, this pressure gradient, this density gradient is now going to cause the diffusion, of particles from the high pressure, high density region, to the low pressure, low density region. So in this case here, this is going to cause lower temperature air particles to move inland, giving us these cooler breezes. So as this Pearls Before Swine cartoon nicely illustrates here, a lot of what happens in our physical world can be explained by the concept, and it's very often said, nature abhors a vacuum. And as the comic suggests, a vacuum really represents a pressure gradient. But if we kind of expand this and think of this very generally, nature really abhors any type of gradient, whether it's a pressure gradient, a density gradient, a temperature gradient, an energy gradient. And the way that nature tends to respond to a gradient of any form, is to try to minimize it. So really, this can explain a lot of why things happen in our universe. When you see that gradients exist and nature responds, by trying to minimize or eliminate, that difference or that gradient. So another example, a rather important one to us, is the ability to be able to heat water in a pot. How does the water get heated? Well, let's take a look at Bongo's clam pot from our opening slide here and take a closer look at what's happening inside of that pot with the water. So, there we go. So what happens is that the water on the bottom of the pot may get heated by thermal conduction along with the metal in the bottom of the pot. But that water on the bottom will, once it gets heated, will rise because it becomes less dense and more buoyant than the cooler water above it. And what you see here, these circular convection currents get set up. So the warm water rises up, but as it rises up, it cools off, becomes more dense, and then will end up falling again, only to have this process repeated. So this is how you get these circulating convection currents set up in a fluid. Another nice illustration of this is the lava lamp. Many of you may have seen these or even had one before, but here you can see that there is a light bulb on the bottom of the lamp, and when you turn on that light bulb, it heats the water on the bottom portion of the lamp, mostly by conduction and, as we'll see, radiation. But once that water on the bottom of the container gets heated, it becomes less dense and more buoyant. It will rise up, to the top, and as it rises up, along with the globular gel that's in there, it will cool, become more dense and sink again. So with the gel-like blob, you can nicely see what's going on in terms of convection. You see the decrease in density, the increase in buoyancy, but as the fluid rises up, it becomes more dense and less buoyant, and so it sinks again, falls down to the bottom, gets heated up, and this process repeats. So, like I said, this rising and subsequent falling of the fluid is what we refer to as a convection current. So another example we'll look at involving natural convection is that of radiant heating in homes. Let's take a look at a couple simulations here. Did you ever wonder why the radiator is placed near the floor rather than the ceiling? Well, think about how this process works. The air that's in contact with a warm radiator, okay, rises because it becomes less dense and more buoyant, allowing the cooler air to come in and take its place. So as that warm air rises, it will naturally spread out and will cool off in the process, become more dense and sink. So as these simulations nicely illustrate, you get these circular convection currents, okay, that get set up to circulate the air in your house.
One of the methods of thermal energy transfer is that of convection, which involves the mass movement of particles from one point in space to another. So this is a convection of gases demo, which will nicely illustrate not only convection, but the convection currents that get set up. So what we have here is we have a lit candle, and above that lit candle is a chimney, okay? Somewhere over here in a chamber further away from the heat source, we have another chimney, okay? Notice that this is since there is no heat source, that represents a cool portion in space. And we will start by observing, okay, the flow of the particles above the heat source. And notice that the air in contact with the candle warms up, it heats up, okay, becomes less dense and more buoyant, and it rises up. And you can see that, even though you can't see the air, we will put some smoke with this incense in our chimney here. Okay, and you might see a little bit of the air moving up, the smoke moving upwards, okay, along with the air, showing the direction of its movement. Okay, now we're now going to take a look at is the effect of, okay, the convection current in the cooler portion of space. Notice when I put this burning incense in the chimney here, okay, that is not above the heat source, notice the draw, notice the movement of the smoke and the air, okay, downwards, right? So the air here, the cooler air becomes, which is more dense, okay, less buoyant, sinks, and you can see the formation of these circular convection currents that will transport particles from one point in space to another.
So let's see if we can use what we know about natural convection and advection to explain this convection of gases demonstration. So you recall what we observed first was what happened when we held the lighted split or wick, okay, over the chimney where there was no lit candle underneath. And we observed that the smoke moved randomly over the chimney opening. Okay, that the smoke particles naturally diffused in all directions, not in any preferred direction. Okay, when we next put a lit candle under one of the chimneys and held a lighted splint, okay, above that chimney, what did we observe? Okay, now we observed the smoke moved upwards. And this could be explained by convection, right? The air above the lit candle heated up, okay, got warmer and therefore less dense and more buoyant, causing it to rise upwards, okay, taking the smoke particles right along with it. All right, so what happened when we now held the splint or wick, okay, above the chimney with the unlit candle? Okay, and this is where we saw the advection come into play. This is where we saw the delta breeze really on a much smaller scale. Okay, so we saw the smoke actually move downwards, okay, and a circular convection current got set up. So think about it. The downward and horizontal motion of those smoke particles and the air was due to the fact that we have this pressure and density gradient set up. Right? The air above the region of the lit candle over here is less dense and has a lower pressure, okay, than the air over in this cooler side of the box, okay, where the air is more dense and has a higher pressure. This causes the diffusion of the air particles and smoke particles, okay, from the colder region to the warmer region. So you can see here that we get the rising of the smoke and air due to the convection and the subsequent falling and horizontal movement of the air due to the advection, creating these circular convection currents. So we talked about something cool you could do with a cigarette earlier in today's lesson. Okay, here's something cool you can do with a match, or really a couple of matches, and this is what I call the convection tester. So try this out sometime, because it's really a great little activity or demonstration to see, okay, convection in action, to actually believe in convection. So here's what you need to do. Take a lit candle and take 2 matches, and you're going to position those matches in different locations around that candle. So position 1 match on the side of the candle and another match directly above the candle. And what you're going to notice is that because of the natural convection that takes place, okay, the natural rising action of that less dense, more buoyant air, that is going to cause heat transfer upwards. Okay, and you will see that that match held above the candle will light, okay, before the match that is held beside the candle. Okay, heat transfer by convection, folks.
So we will now revisit the radiometer, because this third method of heat, that is energy transfer due to a temperature difference, is one you're already familiar with. It is energy transfer in the form of electromagnetic waves that we now give the name radiation. While both conduction and convection require a medium for transfer, electromagnetic waves, as y'all know, can transfer through empty space even when no matter is present. Okay, while electromagnetic waves can have a variety of frequencies and energies, when these waves interact with matter, some of their energy will increase the random motion of the particles themselves. In other words, increasing the internal energy of the particles. This transfer of energy in the form of electromagnetic waves is thus a form of heat.
So on this slide, I'm going to summarize the main points that I stated in the video clip on the previous slide. So to understand what this third method of heat transfer is, energy transfer, that we call radiation, we would say that radiation is a method of heat or energy transfer by means of electromagnetic waves, okay, a concept we're already very familiar with. So what causes heat transfer by radiation? The real question is, what causes electromagnetic waves to be created? And really, it's vibrating charged particles, okay, that create electromagnetic waves. I say vibrating charged particles. In general, it's accelerating charged particles. And this is something you'll talk in great detail about in Physics 103. Okay, but a vibration, as you know, is an example of an acceleration. So any particle that vibrates back and forth accelerates. Anytime a charged particle accelerates, it creates an electromagnetic wave, okay, which will transfer energy from one point in space to another. Now, since all objects contain charged particles, and unless this object is at absolute zero, you know that the kinetic molecular theory says that those particles are in constant motion. So even at low temperatures where your objects are in a solid state, okay, all solids consist of charged particles that vibrate. Therefore, all objects emit radiation. When we contrast this third method of heat transfer to conduction and convection, okay, the most important difference to never forget is that both conduction and convection require the presence of matter for an energy transfer. But radiation, as you know electromagnetic waves, although they can travel through matter, okay, they do not require matter, okay, to travel. Electromagnetic waves can travel through empty space. So this is the only method of heat transfer that can take place in the absence of matter. So just looking at revisiting an example that we talked about before, okay, we saw that heating a pot of water on the stove. Okay, this looks like an electric stove with an electric heating element. That while the transfer of energy from the heating coil to the metal pot is taking place mostly via thermal conduction, okay, while the heating of the water is taking place mostly because of convection. Okay, notice that the heating of the room due to the heating coil on the stove, that is due to radiation. Inside that heating element, inside that heating coil, okay, the vibration, the back and forth motion of those electrons is creating electromagnetic waves, and those waves are traveling throughout the room, okay, and we'll talk more about those waves that are in the infrared region of this electromagnetic spectrum we consider to be heat, but even waves that are above or below those frequencies, when they get absorbed by matter, will end up in the form of heat. So in general, we will say that while we think of thermal conduction as being very similar to a mechanical wave, energy transfer by a mechanical wave, and convection as being a method of energy transfer by particles, we now see that radiation is a method of energy transfer by electromagnetic waves. So recall that when we talked about thermal conduction, we had an empirical law, to describe the rate at which energy got transferred, by this method of energy transfer we call conduction. We're going to do exactly the same thing here. We're going to talk about an empirical law that describes the rate at which energy gets transferred by radiation. And this law, it's quantitative. It will allow us to make predictions and to be able to get some quantitative information about systems. So this is what we call the Stephen-Boltzmann law. It's written like this, and we're now going to go through what each of these quantities means. So P is, as we would expect, is a measure of power. It's the rate at which energy gets transferred by radiation. It is the amount of energy transferred by this method of heat transfer per unit time. The rate at which energy gets transferred by radiation. Sigma is what we call the Stephen-Boltzmann constant, the founder of this law. It is a universal constant. Unlike when we talked about the constant for thermal conductivity in that empirical law, that was not a universal constant. K, recall, depended upon the type of material. Sigma, however, is a universal constant, does not depend upon the material type. It would have the same value anywhere in the universe for any material. A is what we would consider to be the surface area of the object. So for example, if you wanted to figure out how much energy gets radiated per unit time from a distant star, A would now represent the surface area of that star. T is temperature, but not just any old temperature, it's the absolute or Kelvin temperature of the object. So we see here that the energy radiated, the power radiated depends upon the temperature of the object. Goes like temperature to the fourth power. That's huge. The higher the temperature, the much more energy transfer, in this form, of radiation as the temperature of the object increases. So you can imagine a very hot star is going to transfer a lot of energy per unit time in this form, radiation. E is what we call the emissivity constant, and we'll talk in just a second about what it means. How about right now? So when we look at the properties of the emissivity constant has a range of values anywhere from 0 to 1. And it turns out that black surfaces have emissivity values very close to 1, while very shiny surfaces have emissivity values very close to 0. Why? Well, I think many of you probably know this, but an object appears black, okay, because it does not reflect light. In other words, a black object absorbs all of the light on it. Since it doesn't reflect any back into your eye, it appears black. In other words, black is the absence of reflected light. Whereas a very shiny, silvery, mirror-like surface, okay, reflects almost all of the light from it, so it's going to have an emissivity value close to 0. Note here that E, the emissivity constant, depends upon the material type. Okay, so it is not a universal constant like the Stephen Boltzmann constant. It's more like the thermal conductivity K value, which also depends upon material type. It turns out that a good emitter of radiation, okay, is also a good absorber of radiation and vice versa. So when we talk about a black body, that is a term that we use. It is really an idealized term. It's never actually realized, but a perfect black body would be a perfect emitter and absorber of radiation. It turns out that metallic surfaces, which are very poor absorbers and poor emitters of radiation, as we said, have emissivity values, okay, close to 0. So it should be noted that all objects emit radiation in a mixture of frequencies and wavelengths. And as we'll talk in a little bit, okay, we'll say in a little bit that an object emits radiation, but the frequency or wavelength of the radiation that is most significant, okay, will depend upon the temperature of the object. Infrared radiation absorbed by the skin produces a sensation of heat. So infrared radiation is commonly referred to as heat radiation. And remember that the infrared portion of the electromagnetic spectrum is slightly lower in frequency than that of visible light. As the temperature of an object increases, it emits more radiation in the shorter wavelength, higher frequency end of the spectrum. Okay, and this is what we were talking about on point A above. So let's just take a look at a couple of examples of this. And if we compare the Earth to coals in a fireplace to a hot metal object, the Earth represents a relatively cool or low temperature object. So most of the radiation emitted by the Earth is in the long wavelength, low frequency region below visible light. Whereas when you look at coals in a fireplace, why is it that they glow red? Okay, well, now they glow red because they're emitting a lot, at that temperature, they're emitting a lot of radiation in the visible red portion of the electromagnetic spectrum. Okay, when you look at a very hot metal object, which is at an even higher temperature, okay, it is emitting a lot more radiation in the higher end of the visible region of the electromagnetic spectrum. Okay, that is a higher frequency end, lower wavelength end. So in the yellow to blue portion of the spectrum. So while any object will emit, all different wavelengths and all different frequencies of electromagnetic waves, okay, the frequency that is most common, okay, will depend upon the temperature. And as we're saying, as the temperature increases, okay, an object is going to emit more radiation in the higher frequency, lower wavelength portion of the electromagnetic spectrum. So radiation as a method of heat transfer is not typically significant at low temperatures, okay, but becomes significant at higher temperatures. So, for example, a house will lose very little heat, okay, through radiation, while a light bulb, which is at a much higher temperature, several thousand degrees Celsius, will emit, okay, most of its heat to the environment, okay, through this method of energy transfer, through radiation. So the last thing we'll say about this topic before turning our attention to solving some problems, okay, is that when you apply the Stephen Boltzmann law, you have to look at the net energy transfer by radiation. It turns out that not only does every object emit radiation as determined by the Stephen-Boltzmann law, but also every object absorbs radiation from its environment, okay, so long as that environment is at a different temperature from the object. So we really need to look at, okay, both the radiation emitted by the object as well as the radiation absorbed when applying the Stephen-Boltzmann law. So we can say that the net rate of radiant heat flow, okay, radiant energy transfer, would be equal to, okay, the power emitted by the object in question, the power emitted by your system, minus the power absorbed by your system. Remember, power is simply, okay, the amount of energy transferred per unit time. So just plugging this into the Stephen-Boltzmann law, okay, we see here that, okay, this term over here simply represents the power emitted by your object, whereas this term here represents the power absorbed by your object. So here, typically, you know, if you're, I mean, we can use this in all cases, but a typical problem would involve the object being at a higher temperature than the environment itself. So we can certainly factor out those common factors here and write it like this, okay? An expression for the Stephen-Boltzmann law giving us the net power radiated by an object. So we will now turn our attention to some examples involving this very important method of heat transfer that we call radiation. Starting with perhaps the most important example, which gives us life here on Earth. Okay, without this method of heat transfer, life, you, me, would not be possible. So the daily warming of the Earth. The Earth warms each day as a result of the radiation that gets transferred to the Earth from the sun. Think about it. This energy travels 93 million miles through, okay, mostly empty space, and therefore could not be transferred, okay, by either conduction or convection, which both require a medium for transport. Radiant energy reaches the Earth in the form of electromagnetic waves consisting of a variety of frequencies and variety of wavelengths. Okay, good thing for us. And just because I didn't want to create a whole other slide, another example here, think about, okay, the warming that might take place not from the sun but from a typical campfire. If you're not going to be, you know, positioned above the fire, if you're going to be positioned horizontally, how is that energy getting transferred to your body? Almost entirely through radiation. Remember, the air between you and the campfire is a good insulator, so you're not getting a whole lot of heat transfer by thermal conduction, nor are you getting a whole lot of heat transfer by convection. But in that fireplace, okay, the electromagnetic waves that are being created by those accelerating charged particles, those electromagnetic waves are traveling and hitting your body, okay, and transferring energy to your body in the process. So thermography is a diagnostic technique used in medicine, okay, whereby an instrument called a thermograph measures the intensity of radiation emitted from, okay, various points in the body, okay, forming a picture that resembles an X-ray. Areas where the metabolic activity is high, okay, such as with tumors, okay, can be detected on a thermogram as a result of the higher temperature and increased amount of, okay, radiation and, as I said, metabolic activity. So you see here in the upper right, this is an example of a thermogram, and it will show you, okay, different colored regions suggesting different temperatures at different points in the human body. If you look at the thermogram on the lower right, okay, you can see that the increased metabolic activity in the woman's breast, okay, suggests evidence of a tumor there. So this is how it can be used as a diagnostic technique. And when you look at your lower left, okay, I really have no idea what that is. I guess they captured a little dinosaur and okay, did some thermography on it. Okay, there you see a thermogram of it. I would assume it's a simulation. I don't know where it came from, but when I was searching for images, I found it. I thought it was pretty cool, and so I'd include it here. So look in the next slide. I will show you a demonstration. If you've never heard a remote control, a TV remote control before, you'll get a chance to hear it on the next slide. I actually created it for a demonstration in energy conversions. But if you're wondering, how does the remote mechanism work? Okay, well, it actually creates photons in the infrared region of the electromagnetic spectrum. And if we think about this in terms of waves, okay, it's electromagnetic waves in the infrared region of the spectrum, which are sent from the remote transmitter, okay, to the receiver in the television. So you may not think about it, but once again, energy transfer by radiation. So, feel free to, fast forward through the part. Okay, but I'll show you how a remote control can be used to activate, in this case, a speaker, okay, using a solar cell.
Now, how many of you have ever actually heard your remote control before? Well, today you're going to get a chance to actually hear a remote control. I'm going to use this to demonstrate some energy conversions, some energy transformations. And there's quite a few that take place here. We'll focus on a few that are taking place in this remote control. Let me explain a little bit about our setup here. What we have here is a solar cell. This might be like the cell you'd find on an outdoor solar light. And we've attached this high-quality Radio Shack speaker to it. Let me turn it on here. Okay, we have a little bit of background light which is hitting this cell. You probably can't hear it from there, but it's causing a little bit of background static in that speaker. But if I take this remote control and I aim it at the solar cell, I'm going to shoot little particles of light called photons at the cell, and it's going to activate the speaker here. Let's see how that works. You get that sort of Star Wars effect. So you're actually hearing the remote control. Quite fun. Now, the energy transformations I'm talking about, let's start with this remote here. Well, certainly in the back you see there's batteries. So the electrostatic potential energy that's stored in these batteries gets converted to electrical energy. When we get those electrons moving, that's what we call an electric current. So we've got electrostatic potential energy being converted into electrical energy, the kinetic energy moving electrons, which get converted into radiant energy or light. And it turns out that this remote control will send out little particles of light, little photons, in the infrared region of the electromagnetic spectrum. So your eye's not sensitive to those. You can't actually see them. But certainly the solar cell can.
So in this slide, we'll take a look at the operation of a Dewar flask. And I know that although, the Dewar was the original invention in this country, the flask has been branded with the brand name Thermos. But a Dewar flask is a double-walled evacuated Pyrex glass vessel with silvered walls. And the reason I'm talking about it here is because it really involves all methods of heat transfer that we've talked about today. So it's a good example to see all methods of heat transfer in action. And the purpose of the Dewar flask is to keep liquids either hot or cold. It's to prevent internal energy transfer to the environment. So you see here in the illustration, you see the Dewar flask, the various parts. So what do we have here? Well, we have a Pyrex container, and in that Pyrex container we have it, you see where it says vacuum here, it is partially evacuated. Remember that in order to have energy or heat transfer by conduction or convection, you must have matter. So the evacuation of that chamber region, okay, means that you are going to minimize or eliminate heat loss through both conduction and convection. And I don't know if any of you have ever had the experience of dropping a Dewar flask, but when you drop it, they have a tendency to explode. And that explosion is what happens when, basically that vacuum is being broken. Okay, it creates a very loud sound, okay, when it's broken, when the Pyrex shatters. So we talked about conduction and convection there. What about radiation? Well, you see here it says glass walls with a silvered surface. If you look at the inside of the typical Dewar flask, you'll see that it looks silvery. Those walls are silver. Well, think about what we said about the emissivity constant. Having silver walls means that the emissivity constant, okay, has a value very close to 0. Therefore, that means you are going to have very little heat transfer, okay, through those walls due to radiation. Okay, when electromagnetic waves hit those walls, they will get reflected rather than transmitted, okay, because those silver walls means that, okay, it will not be a good absorber of radiation, but will rather be a reflector of radiation. So that's the idea with that, so the silver walls. So, okay, using all 3 methods of energy transfer in this design, okay, you are basically eliminating or really minimizing the transfer of heat, okay, with all of these methods, meaning that, okay, if you've got a cold liquid in there, okay, you should prevent transfer of energy from the environment to the liquid. And if you've got a hot liquid in there, you should prevent transfer, okay, from the liquid to the lower temperature environment. So this is my opinion, of course, but I believe that to be a functionally aware citizen in today's society, you should have a basic understanding of the greenhouse effect, okay, the root cause of global warming. So that is what we're going to review in this slide. Hopefully you already have some understanding of this from, okay, prior science courses. So let's take a look. We said in a previous slide that the Earth receives all of its energy from the sun in the form of radiation. Okay, so these electromagnetic waves from the sun strike the Earth, and because the sun is at a high temperature, remember the Stephen Boltzmann law says that for high temperature objects, they will emit much more radiation in the high frequency short wavelength end of the spectrum. And it turns out that our atmosphere is quite transparent to high frequency electromagnetic waves getting through. So these waves are absorbed by our atmosphere and Earth, okay, rather than reflected. And when those waves come and they get absorbed by the Earth, okay, they get re-radiated in a much lower frequency, longer wavelength end of the spectrum. So think about what the Stephen Boltzmann law says. The Earth is at a much lower temperature than the sun, so it will emit much more radiation in the lower frequency range. The problem is that, okay, these lower frequency electromagnetic waves, as you can see in the simulation, okay, do not actually, okay, repenetrate the Earth's atmosphere and travel out into space. In certain atmospheric gases like carbon dioxide and water, and certainly methane and other gases, actually absorb this low frequency radiation and re-radiate it back to Earth rather than allowing it to, okay, go back out into space. And this re-radiation, this absorption or re-radiation back to Earth, causes the warming of the Earth. So as we said, it turns out that the Earth's atmosphere is quite transparent, okay, to high frequency radiation, whereas it tends to absorb, okay, and not transmit lower frequency radiation. And this is a problem, okay? Think about it. If the Earth is able to, on a daily basis, absorb more energy than it is able to re-emit, it is going to gradually warm in time. So the increased level of greenhouse gases due to the industrialization of our societies, okay, is contributing to this problem, right? It's creating these gases in the atmosphere that are not allowing, okay, those electromagnetic waves to escape. If you're saying, what does this have to do with greenhouses? Okay, well, it's okay, a very similar phenomenon. In greenhouses, it's the glass rather than the atmosphere that acts as this one-way valve. Okay, it allows visible light in the higher frequency, okay, portions of the spectrum to penetrate the greenhouse. Okay, but once it gets absorbed, okay, by the plants, it is re-radiated in a lower portion of the spectrum that cannot get repenetrated. Okay, that gets reflected back, okay, into the greenhouse, thus causing it to warm up. Now, in the case of a greenhouse, that's a good thing, okay, because in the wintertime, you can keep plants alive in the greenhouse so long as you have sun shining in the day. Okay, but for our Earth, the greenhouse effect is causing this problem of global warming. Right, we will finish off with a couple quantitative examples, okay, using the Stephen-Boltzmann law. So the first example we'll take a look at is, okay, radiation by the human body. So here it says, suppose that your skin has an emissivity constant of 0.7, a temperature of 34 degrees Celsius, in a total area of 1.6 square meters. Calculate the power of radiated energy from your skin when the ambient room temperature is 25 degrees Celsius. So here we have to remember that your body is not only emitting radiation to the lower temperature room, but it is also absorbing radiation from the room itself. So we have to look at, okay, not only the power radiated, but also the power absorbed, according to the Stephen-Boltzmann law. So here it is. Here's the expression for the net transfer of heat by radiation. And we see here that the Stephen-Boltzmann constant, okay, has this value here, 5.67 times 10 to the minus 8 watts per meter squared Kelvin to the fourth. Okay, that's sigma. The emissivity constant is 0.7. Okay, that's for your skin. It's your skin that's in contact with the room. A, that would represent the total surface area of your skin, since you are pretty much radiating energy from all parts of your skin. Okay, so that's the 1.6 meters squared. And then don't forget, you got to make sure that you're dealing in absolute temperature. Okay, if your body temperature is at 34 degrees Celsius, that's 307 Kelvin. Okay, the ambient room temperature is 25 degrees Celsius or 298 Kelvin. Of course, we've got to raise those to the fourth power. When you do the number crunching, you come out with a net power radiated to the room of 63 watts. So you in a sense, your body, you're behaving as like a 60-watt light bulb. Okay. Obviously, you've got to make sure that you can metabolize food to be able to replace this energy, because, okay, without the consumption of food, okay, your body is losing quite a bit of energy every second, which needs to get replaced. So in this last example, we will use the Stephen-Boltzmann law to be able to estimate the sun's temperature. So we are told here that the sun radiates energy at the rate of 3.9 times 10 to the 26 watts. Okay, and this is a calculation you can do by measuring, okay, the amount of energy transfer to a small section of the Earth, and then, okay, extrapolating, treating the sun as a sphere. Okay, and given that the sun's radius is 7 times 10 to the 8th meters. So we're going to assume that the sun is a perfect black body. Remember, it is a perfect absorber and perfect emitter of radiation, which would, okay, imply that it has an emissivity constant of 1. Okay, from this we can estimate the sun's surface temperature. So Stephen-Boltzmann's law says this, okay, we are going to assume that, okay, whatever the temperature of the environment is, it's extremely small compared to that of the sun. Okay, we're talking about empty space, so we will only look at the power radiated. Okay. And according to the Stevens-Boltzmann's law, we will solve for temperature. That means taking the fourth root of the power divided by the emissivity constant divided by the Boltzmann constant divided by the surface area of the sun. And by the way, the surface area of the sun, okay, you will see over here, okay, we are writing as 4 pi r squared since we're given the radius of the sun. So, substituting in our numbers here, okay, the power, 3.9 times 10 to the 26 watts, emissivity constant of 1, okay, Stevens-Boltzmann constant, 4 pi times the radius of the sun squared, okay, and we do the number crunching and we come up with an estimate of, okay, 5,800 Kelvin. So just want to make a point here that the surface of the sun, okay, it's hot, okay, but 5,800 Kelvin, not nearly as hot as the interior of the sun, which is several hundred million Kelvin, okay, due to the extreme pressures and temperatures there.